Hi, hello everybody, GreatCorn's here. Some time ago I released a video detailing the process of creating a 3D horror game using assembly. I don't know why I pronounce it like assembly. In my native language it's literally assembler.
Мова асемблера.
That video has become the most viewed one on my channel, garnering around 149,000 views as of now, for which I'm very thankful to you. The video highlighted the challenges of working with assembly despite the various macros and quality of life features that the Microsoft Macro Assembler provides. The video's ending even had me go insane due to the comparatively shallow results that required even more effort because of the assembly environment. In reality, my mental health truly wasn't in the best shape at the time, but only partially due to coding. My sleep schedule was messed up, mostly inverted, where I would wake up and code at night in quiet peace and have trouble sleeping during the day, having dreams about the code due to my mind being so preoccupied with it. But since then, I have pretty much finished MASM's 3D, the quote-unquote game I was working on, with it getting at least 2 endings, around 13 characters in total, and even a small animation project based on it. For most normal people, this kind of ordeal would likely be a one-time experience, where they would use the knowledge they gained coding in assembly elsewhere, in more practical and sane environments, ranging from full-blown game engines to, at the very least, more platform-agnostic and optimizable programming languages like C, Pascal, Rust, that have their libraries ported across many different systems. I am not among those people. After finishing MASM's 3D, I was able to get some refreshment from the state that Ukraine was in, and still is even more so now than ever, by traveling to Italy for an educational program. What I had with me for work was an old Dell Vostro laptop that my dear friend had lent and later gifted to me, with an Intel Celeron CPU and no dedicated graphics. Half-Life lacked on the thing, for Christ's sake. Having a lot of free time, being in a rural town of an unfamiliar country with a stunning seashore and remarkable antique architecture, I did the most logical thing I could. Stayed at home and spent my time programming an assembly with OpenGL and WinAPI. And playing Strife.
Oh gee, now look what you've done.
Some people have asked me if or why I've stopped programming. The truth is, I didn't. It just takes a really long time for me to do anything game-related, because now I want to do it properly, pretty much from scratch, and still in the same MASM-compatible environment. For example, this godforsaken piece of Stroopwafel and its underlying engine have been in the works from the end of 2024, passed through development on 3 different computers, 2 different countries, at least 3 different operating systems, and, well, for the game part, it's still not even near a proper presentable demo state. I wanted to shape it up into a proper demo, but that would have kept this video in limbo for many more months, maybe even years. But why assembly again? It's actually a question to which I had trouble finding the answer myself. Is it just pretentiousness? Do I think I'm somehow better than others by doing things through unnecessarily complicated methodology? Did I somehow manage to get used to coding in MASM-compatible x86? Yes. Well, first of all, assembly isn't really some scary insurmountable beast. Once you get through the basics, or if you've had enough experience with lower than average level programming in other languages, you could get used to it pretty quickly. I'm not saying that I've mastered it, I still really have a lot to learn about it, but whatever I'm doing with it right now also isn't a very complicated programming task, especially when simplified with OpenGL, WinAPI and OpenL. Of course, the difficulties you may need to overcome will vary depending on your exact ideas and needs, but I've seen some projects made on high-end game engines that wouldn't require too much feature implementation outside of them. And don't let the blandness of MASM's 3D's gameplay and visual look show what a game written in assembly is limited to, because in my case it just boils down to me not being good at making fun games, rather than an inherent quality of how the game was coded. Most people resort to assembly for very specific, hardware-related tasks. for direct control over each operation where a higher level language compiler could fail or would impose its own rules. In very rare cases, assembly is preferred for maximum performance optimization, as it has the potential for lightning-fast code, though mostly if a compiler wouldn't otherwise provide it and if the programmer is fully aware of what exactly they are doing and of the environment their program is designed to work in. This knowledge of what exactly is going on is, I think, a detail that embodies the main principle of assembly and why I particularly enjoy it, other than just having been used to it. When programming in such a low-level language, even with components like the Windows API and OpenGL, you're pretty much fully in control of the code and responsible for every operation, error, and bug. In most cases, when I encountered problems, they were due to my own blunders and not some quirk with the API I was using. You manage all the overhead that is to be created, and MASM expands on this, though not being directly comparable to a higher-level programming language, but allowing for conscious, responsible abstraction using its built-in preprocessor functionality. That functionality includes the macros. What they entail is explained in the term itself. Pre in preprocessor signifies before. Here it means processing specific code before its compilation and building. This means that the macros are something like inline functions. They get expanded into code on each call, and that allows for some intricate practices, but more on that later. You may apply the core paradigms that you want for generalization. Some people even implemented object-oriented programming functionality into it, which I also kind of followed in certain cases. Reiterating once again on the topic of practically everything being under the programmer's control, the maximum proper generalization proves to be of utmost importance, as to reduce the amount of code and program structure that the programmer has to keep in their head. In programming, generalization means finding common recurrent patterns in the code and sorting them into their own functions to be called instead of the spaghetti, therefore sorting the code out and making it easier to navigate. In any case, working with x86 also exercises an exhausting degree of attention needed to be kept, as a single small mistake, like forgetting to pop a stack, might result in problems from the most unexpected places. But as humans are prone to error, I am no stranger to such situations, and the capabilities for extensive debugging are necessary. The most useful tool to search for exception culprits for me was the good old WinDebug. Working directly in x86 with few abstractions, its disassembly gave me a way to directly see which line of code would cause errors, and the call stack would show in which procedure it's located, provided the symbolic names are exported. However, sometimes the bugs wouldn't cause any exceptions to be raised, and then the tracing process would be a little harder, because I'd mostly be on my own with it. Most such bugs would occur with the floating point unit, due to invalid operations with its own stack that it has, like forgetting to pop it or popping it more than I've loaded into it. The FPU does have a code word with many different bit flags, and 6 of them concern exception masking. Demasking the invalid operations would trigger the respective exceptions to be raised, but more often than not, they wouldn't be traced to the point in code where I made my mistake. Now, I will remind you that it is not inherently a fault of the FPU. For example, if I load more values onto the FPU stack than I pop out of it, the exception would trigger whenever the stack would overflow. But that overflow might not happen at the point in the code where the disbalancing took place, because it could be a singular occurrence in the main loop of the game. Another possible untraceable problem could be a jump to an invalid location, like a label or a function, where the debugger's call stack would freak out and not help me at all. Such cases lead me to manually brute force my way through the code with print macros, but somehow, so far, all of those would end up with positive results, and there never was a time in my life where I had to re-examine the entire code of my games. To help with this, I also coded a tiny low-level procedure profiler, though this mostly stemmed from me wanting to see how long the execution of each procedure takes for optimization goals. This was done by setting custom procedure prologues and epilogues, which MASM allows you to do pretty easily. A procedure's prologue and epilogue are bits of automatic code added in the header and footer of a procedure's, otherwise a function's, declaration to create a stack frame, set up the stack for past arguments and local variables, and then at the end return to the call location, maybe free the stack and do other nuances which are based around the calling conventions. This allowed me to insert timestamp operations in procedures, for example from a list of source files, without modifying each and every one of them by themselves. Just like in the MASM's 3D video, if we want to play around with OpenGL or create a game that uses it, we likely need to make a window first. Not knowing how relatively trivial static linking DLLs in MASM could be, I wanted to find a way to generalize all of the boilerplate Vim API code needed to initialize a working OpenGL environment in it. So I started making a framework library for MASM called Boilerplate 3D, which would provide a simple forms-like interface to create a window and an OpenGL context within it, with as few reused lines of code as possible. The main challenge of the library as a whole was the process of generalization, balancing between the necessary feature-complete flexibility and the over-complexity of usage, while maintaining as much parity between different platforms as I could. You heard it right. Some might have thought that if I program an x86 MASM, that means I only intend to support Windows. First of all, I definitely would never support what Microsoft has been doing with its OS lately, and secondly, well, that would still not really be the case. While the Microsoft macro assembler, unlike MASM, one of the most popular assemblers for x86, is bound to DOS and Windows only, there are solutions to make the code written for it work on other systems, and they are not as complicated as you may think. First of all, MASM itself isn't the only MASM-compatible assembler and set of tools. The list includes the Borland Turbo Assembler, the Pelles macro assembler, Nidod's ASM-C macro assembler, the TerraSpace UASM based on JWASM, among others. All of these more or less support the MASM macro syntax and preprocessor functionality, and some are fully open source and available for platforms other than Windows. As for the headers, UASM also supplies the WinInc header package, which contains Windows C headers properly converted into MASM include files. The headers that MASM supplied are DLL-based, pretty barren, and don't have proper time declarations, especially limiting pointers to 32-bit only. The conversion is done using the H2IncX tool, which also helped me with importing OpenAL headers. Technically, it would be possible to code the framework library in parallel for the Windows API and others, such as the X Windows server with the Linux kernel, however that would be a bit too complicated for me, as I'm mostly completely unfamiliar with programming for other operating systems. Seemingly, the other option would be to target different versions of Windows and compatibility layers like Wine, which is what I ended up doing. For now, the framework is compilable with MASM, SMC and UASM. Works natively on Windows versions from 98 Special Edition to 11 tested, ReactOS and Wine tested on Linux, FreeBSD and Android through WinLater. In fact, most of the code for it and the games that use it were written and compiled through Wine on Debian Linux. Yes, I even used Notepad++ through Wine to write it. This approach may also come with its own advantage. If the compatibility layer is properly ported and supported on a foreign operating system, I can use the best practices for Windows, squeeze the most optimizations, and, at least if using the fixed function OpenGL pipeline, have virtually identical visual representation of my project across many different setups. As for performance, on that same Celeron laptop, the games would somehow run smoother and faster through Wine, rather than in a native environment.
Дайте мне, пожалуйста, Windows с кернелем от Wine.
Development for Boilerplate 3D began alongside a game project, which is often ill-advised in the game dev community, because, not counting the obvious difficulties with making your own engine, the focus splits between competing needs, and there's either the risk of the engine ending up with many niche, situational features that would hinder the concept of generalization, or the risk of negatively affecting the creative process, due to the constant engineering of the technical aspects, making the game incredibly basic and bare bones. I wanted to shape up some kind of proper demo for the framework to come alongside this video. First it was the project you saw before, but I realized it would take entirely too long to make it into something that I would consider presentable and worthwhile, even for a demo. There's also a lot of engine-specific components in that game that I'm still thinking if I should implement into the base framework or not, like the weird segmented collisions, the particle systems, UI, visual effects, multiplayer? Wait, no. That comes from the next thing I wanted to do, which was to rewrite MASM's 3D completely from scratch, with the usage of the framework, for better code structure and compatibility reasons. But then my critical consciousness came into play and I started adding new features, wanting to expand on the game's initial blandness. I started adding a freaking multiplayer mode, and then my critical consciousness finally told me that the core gameplay sucked ass, and if I wanted something truly fun to play, then I had to spend even more time on it, because maybe even if I learned how to make games, I'm still horrible at making games. I'm sorry. Okay. I've been mentioning the word engine, but previously referred to Boilerplate 3D as both a framework and a library. What is the difference, and what exactly is Boilerplate 3D? Let's start with what a library is. It's often defined as a collection of code that you call when needed, like a toolbox. You decide what you want to build and which specific tool to use. A framework inverts control and calls your code. It's an exoskeleton that actively dictates the structure of your code. It's like a computer case that you can stuff pretty much whatever hardware you want in, but you'd still have to operate within the boundaries of that case. A game engine would be a specialized framework and collection of libraries that provides polished, generalized functionalities commonly expected in games, such as input, rendering, loops, asset loading, physics, etc. It's like a pre-built PC. You generally don't have to worry about getting each component for it and can use it as is, sometimes with possible further customization. Boilerplate 3D is primarily a library, but also incorporates features of a framework and even some of a game engine. I mostly treat it as a framework for game development, but I want to keep it as open and flexible as I can for other uses too. Boilerplate 3D comes as a main library and includes various supplement modules. The main BP3D library focuses on implementing a forms interface with window modes, input processing, basic OpenGL initialization, and game loops with stuff like delta time calculation. It doesn't do much, but it strives to do it with the best possible practices for compatibility and to balance that flexibility with the generalization to reduce boilerplate. That way, it's possible to enforce your own rules upon it, doing custom initialization, processing of the forms, and utilizing other renderers besides OpenGL, or even no renderer at all. The modules come in very different natures, and I'm still debating the necessity of many of them and the absence of others. For now, the most finished are the expected maths and vectors modules that provide useful scalar, floating integer, and vector operations. The maths module allows for such things as demystifying the FPU codeword operations, streamlining the float comparison process, along with a collection of many other useful functions and constants. But the thing that I probably use the most from this module is the immediate float declaration macro. While UASM and probably other assemblers allow for immediate real values in code, MASM requires them to be pre-declared in a data section. This was the case in MASM's 3D, where I had a whole bunch of float numbers pre-declared in a separate include file. The data section could also be interleaved in the code sections, but it wouldn't make declaring them less tedious and ugly. It is also possible to pass immediate real values by their integer IEEE754 representation. If you didn't know, all your float values look kinda like this under the hood, but that hinders the code readability and isn't very convenient either. This is where MASM's macro functionality comes into play. Its macros are a very powerful tool that can pretty much allow you to define your own programming language without runtime overhead. Well, maybe that's an exaggeration, but they do allow you to go pretty deep into the underlying compiler structure. The macros that come pre-packaged with MASM include a macro for such immediate floating point value declaration, but they are kind of clunky and can be memory inefficient, so I just wrote a simple macro that uses the same variable naming scheme as in MASM's 3D and either declares a new float value or passes the identifier if it was declared already. MASM macros also allow for similar functionality with strings, most of which were also pre-declared in data sections in MASM's 3D, but could just be substituted with macros in their immediate locations. The vectors module extends the float functions onto non-scalar compound vector structures, and due to the usage of macros can easily have single definitions for many vector types of different component counts. For example, I just define the main functions in macros and then call these macros in explicit procedures for each vector type, ranging between vector 2, vector 3, vector 4, and also a special type of procedure for vector 3 that uses only the x and z coordinates, omitting the y. This can be handled through macros pretty easily, and if your up coordinate is z, you could also just use the vector2 functions with the vector3 structs. Another module that appeared pretty late into the development of BP3D, but still proved or promised to be useful, is the typedef module. It's intended to be a small shared module that contains some core types and symbolic preprocessor definitions to help generalize boilerplate 3D and its modules further, also supposedly making way for 64-bit compilation by defining specific pointer register types like PAX, PBX, PCX, PDX, etc., instead of using separate, for example, EX and REX. That way, whenever there's a need to keep a pointer, a handle, or otherwise an architecture-specific value in a register, the programmer can use these definitions to keep their code platform agnostic. This feature could be promising, but for now 64-bit compatibility with BP3D remains untested, unfinished, impossible, and generally very rough because the x64 calling convention was made by the devil himself, and in the end offers pretty insignificant advantages over all the problems it produces in the code, and also not to mention the reduced portability. I know that 32-bit wine is becoming a little bit more troublesome on some platforms, like FreeBSD 15. Oh, why did you have to drop the freaking 32-bit package support? Though no worries, I just installed packages from version 14 and it worked flawlessly. Wine worked flawlessly, not FreeBSD, but it's still more preferred by me because of its higher accessibility and predictability when compared to x64. What was I on about? Oh, the modules. Then there come the more unpolished and unfinished modules, ones that I may use pretty extensively but didn't yet bother to finish up for one reason or another. These include the Erase and GL+ modules. The Erase module is supposed to streamline the usage of dynamic multidimensional arrays, but for now I don't use it as much for its intended purposes and haven't yet bothered to implement more than 2 dimensions. A good approach to making it would also be to use an underlying exoskeleton based on macros, but then the structuring orders would have to be accounted for and could quickly spiral into a complicated mess. The GL+ module extends the OpenGL fixed function pipeline functions to include some useful logical variants. The main problem with this module is that most of the function calls are manually extrapolated, and so it is heavily based on the std call calling convention, meaning that it passes all of its arguments through the 32-bit stack and not through some fuck-ass means like here's your integers on the registers, here's your floats on XMM, here's the fucking spaghetti on the rocks, oh and push some of that into the stack cause there's only so many fucking registers. Yeah, I love saving just 1 or 2 fucking CPU ticks out of billions of them per second. Holy shit! The optimization is through the roof! Right. So then there are modules that I really doubt the necessity of because they are mostly hyperspecific and can't be generalized properly. Also, they are the least polished of them all. These are the assets and text modules. Back when developing MASM's 3D, I didn't want to bother with any decoder libraries, so I just invented my own bollocks asset formats. That included models, which were files of binary interleaved UV, normal and vertex data for loading into OpenGL display lists, and textures, which were bad, raw color data in one of the supported OpenGL color formats, which I had to manually specify in code. I had written my own importers for these files because they weren't as complicated, and this extended onto the assets module in BP3D. The model format was split into 2, which by itself isn't a very good idea. The interleaved format was kept the same, but I also introduced a format for dynamic meshes, which just has the same data but with consecutive arrays of UV, normal and vertex data, instead of the interleaved data for each vertex. The dynamic mesh is loaded into separate accessible arrays in a dpmesh struct that are drawn with a generalized function that uses glDrawArrays instead of calling a precompiled list. Dynamic meshes like these allow for, at the very least, vertex animation, which is also what the assets module implements. It has its own animation system with support for PRS, standing for position, rotation and scale, though TRS would probably be more correct where T stands for translation, 4x4 matrix, and vertex animations. The textures format received a major refactor, allowing for more color formats and proper dimensions. The importing process was also improved, as some color formats weren't natively supported on some platforms, so a manual parser was also introduced. Now you might be thinking, with all these custom raw formats, how the hell do I convert something from a proper common asset format into these abominations? How the hell do I animate them or export existing animations into the required format? This is also another problem with the assets module. It can import the custom raw formats but can't really help you create your assets in them. As a workaround for models and textures, I quickly meshed together something like an SDK for myself in Pascal, but for exporting animations I had to go against my basic principles, desecrate my image, my dignity, and commit the worst sin of all. I wrote a Python script in Blender. The texts module, the other one that I mentioned, implements a bare-bones bitmap text renderer with some alignment features. It's just fundamentally structured around the OpenGL fixed function pipeline and uses the assets module to import an array of textures for its fonts. Now the more basic template for a boilerplate 3D project looks like this. You can see that we defined our main form as a bpform struct, then map the offsets, in other words addresses, of the callback functions to the respective struct fields. We set the size that we want and then create our form. This initiates a window processing loop that blocks the execution of any code that follows, up until the form is destroyed and the loop exits. That's why right after the form creation function we have the process termination code. This same or similar logic exists in most object-oriented form APIs, like the Lazarus LCL, Delphi and C++ Builder VCL, C# WinForms, etc. All of the code for our program will have to be put in the previously mentioned callback functions, which encompass form creation, form destruction, different loops, input processing, form resizing, and a specific start callback. The input callback receives a pointer to a struct along with the input type enum. The possible input types right now include joystick or gamepad, axes and buttons, keyboard keys, mouse buttons, and mouse movement. I was planning on including touch input via the raw input Windows API, but for now it's scrapped because of the need to reverse engineer touchscreen drivers. Mouse and joystick input are configurable with the form input flags and can be set to use raw input instead of window messages for mouse and system API for joystick. As mouse input is supported differently across systems, this allows for flexibility and is supposed to fix the common bugs with mouse input, though raw input is not available on Windows 2000 and earlier, but for now there's a special symbolic preprocessor definition to exclude it from the compilation and linking. The main render loop here does all the buffer swapping and delta time calculation behind the scenes. In fact, a lot of crucial underlying processes are automated, but can also be disabled by switching the form's default flag off in the respective callbacks. This could be done to enforce your own way of processing certain form events. In both my game projects, for example, I handle resizing myself to set the rendered viewport size, read the screen texture, and then upscale it for a pixelated look. Boilerplate 3D also comes with a couple of rough demos that illustrate how easy it can be to do some of the basic stuff with its usage, with the biggest one being around 500 lines of code. For comparison, MASM's 3D was around 13,000 lines of code. It even has an example of using DirectX, an object-oriented only API, in pretty much a port of the C++ vertices tutorial, though compilable only with WinInk. They also had their own port of it somewhere online, I believe. But the first and main demo that I wanted to finish and present for the framework was, and with so much work poured into the inner functionality, you'd expect all the focus in it to be more around gameplay and fun, right? Is a planned exploration horror game by me that would focus on atmosphere and non-linear storytelling in a procedural, quasi-open world setting, in other words, yet another walking simulator. Now this sounds a bit too ambitious for a one-man project, especially if coded in assembly, but with only me on the development team, I could take all the time I need to properly implement, develop and polish everything until it's the way I want it to be, without cheaping out whenever it's possible not to. It does give me less motivation to keep it going, having none but my own devalued effort wasted if it's ultimately cancelled, but this is the way I want it to be for now. Some people have their forever worlds in Minecraft, where they just keep on playing the same world for years, taking their time to just enjoy building and developing them. This could be something like a forever world for me in my own environment. I do still plan to release this as a demo first, though I don't yet know if the code for it will be made public. The game's world is a terrain that has 8 different biomes, and my goal for the demo would be to finish every one of them until they are aesthetically consistent and substantive enough to be presented. The main game would expand on these, adding more variety, key locations, as well as the storyline. For now, only 2 of the biomes hold a somewhat believable aesthetic ground, I think. That would be the Sylph forest biome and the Nessie swamp biome. The game plans to feature many structures, most of them in the eastern regions, the Torlak biome, and the inherent abysses. For now, the biggest of them is the church, which is still unfinished and was mostly used to test 3D collisions and large multi-chunk structures. Looking at what makes up the map from the more technical side, the most prominent and important thing here is the terrain system implementation. It is 2D, has data maps for height, biomes along with detail placeability, color, roads, though I plan on rewriting them, arrays of details themselves, and all of that is split into chunks. Regarding the generation, it uses 2D fractal noise for its height and biomes, both Berlin and Voronoi combined in multiple passes, or octaves. Interpolated noise is also applied to the lookup position for distortion. A height fall-off for a river or seashore is also hard-coded to be on the southern edge of the map, and a separate pass is present for small ponds to appear closer to it. Upon generating height, another map for terrain detail placeability is made, also containing information about height plus the biome, which affect how the details are placed and which then gets affected by the details that generate. This is useful, for example, for large trees, which generate only above a certain terrain height level and then set it to a level lower around themselves so as to not have any other such trees generate too close to them, but still allowing for details that can spawn with a lower height level, like grass. Each detail type has its own array for each chunk, which isn't very efficient, but chunks also contain information about the biomes, or aspects, present in them. So any details of aspects that aren't present don't get checked for drawing. Most contemporary 2D terrain systems draw their terrain with a vertex shader that conforms to the height map, maybe a compute shader that would figure out the level of detail, and then use some multi-channel atlas map to apply different ground textures. In my game, I'm using the fixed function OpenGL pipeline that doesn't support shaders, so the terrain itself is drawn with a single texture and vertex color is the only cheap enough way to vary it. As for the height, I could pre-generate each chunk's model and store them as display lists, but drawing them, even the nearest to the player, would still be very performance heavy, and having many small chunks with various LED mesh versions would be more memory consuming, complex, and would have visible seams. I did begin by using a display list approach, but what if there was a better way? I could use a single dynamic pre-configured disk mesh, which has fewer and fewer polygons the further it is from the player. I could attach it to the player's position while snapping it to a grid and transforming the texture matrix, and modify its vertices according to the height. A similar method is also used to draw the water, using a single mesh whose vertices are deformed along the y-axis by a Voronoi pass, though the water doesn't snap to a grid as it is constantly moving either way. It draws multiple meshes, if enabled in the settings, with an animated texture for a more dynamic effect, and also includes a separate pass for shimmer if the player's light is turned on. Looking at the water, you may notice the subtle ripple effect when swimming through, which is done using particle systems. For now, the particle system is quite simple. It allows for looping or one-shot particles with configurable lifetime, velocity, billboarding, and fading. The fading can be distance-based and dot product-based. Both are enabled for the random atmospheric dust particles and make their appearance a little smoother. Distance-based fading means that the particles fade out if the camera gets too close. Dot product-based fading means that the particles fade out if their angle is perpendicular to the camera. This allows for drawing rotatable planes that don't necessarily give away that they're just planes. The water also has a reflection of the sun drawn on it using the stencil buffer, which allows limiting what you render to a cutout mask. This same approach is also used to add terrain holes like in a well structure, as well as the scrollable UI elements. This could also be used to draw proper reflections, but when I tried it, it was finicky, didn't look very good, and in fear of hindering the performance, I abandoned this idea. A small attempt at Fresnel simulation was also made for the water using vertex colors, but is pretty much unnoticeable. In my system, detail objects can be either drawn as display lists or as dynamic BP meshes, which would allow for moving foliage. The details may have a single low LOD version that gets drawn further away and can be billboarded at the camera. Another functionality is detail movability by the player. If a detail that is drawn with a movable flag gets touched by the player, it copies its mesh data, deforms, weirdly, according to the player's relative position, and draws that instead of the normal, or swayed, mesh specified. The details can also have cheap collision functionality, either raising the player's height when in range or prohibiting them from passing through. The collision is limited to distance based only, which means details can only have a circular collider shape. For now, the collision system in the game implements post-factum collisions, meaning that instead of raycasting and affecting velocity, it checks for the collid's position only. This approach probably generally requires less computation effort and is automatically applicable for moving colliders, but its main drawback is that with low enough FPS and thin enough colliders, the collide will simply be able to pass through. Mesh collision is supported, but for now it's mainly through custom-built decomposed convex collision meshes. The swaying, which would most commonly be done through a vertex shader, is instead accomplished by modifying a single mesh, applying translation to its vertices based on the sine and cosine of an incremented value times the y position, so that the vertices closer to the ground modulate less. The deformed mesh is then used to draw all the details of that type. Since the quote-unquote instantiated details are rotated for variety, the swaying directions may contradict each other on some details in close vicinity, but if you don't think too much about it, it just makes it look a little bit more dynamic. Some details have their vertex normals adjusted to face up instead of outwards to make the lighting interaction smoother. Taller details like the trees have a higher draw distance than other details and can also be set up to fade when reaching their terminal draw distance to attempt to reduce popping in. A more versatile development of the detail system is the structure system. While not complex in and of itself, it allows for custom callback procedures for the drawing and processing of the structures that it generates. Each chunk has a dynamic array of structures which can range from simple random fallen trees that just require a different collision box to complex, higher-level interactable multi-chunk areas. Some structures level out the terrain upon generating, some make their elements conform to the height map by either placing singular ones at the appropriate Y level or deforming the dynamic meshes similarly to how the terrain mesh is processed. The player's animations use all three different animation types. The camera's movement is done with the PRS type, without the scale factor, the hands use vertex animations, and the attached objects, like the compass and the flashlight, have their transform modified by a matrix animation. The compass's arrow uses a simple function, something like a damped spring, that controls a velocity variable to gravitate a value to a target. This produces overshoot behavior and can be used for simple physics simulations, like with the Boilerplate 3D soft body demo and the remastered MASM's 3D multiplayer characters Scarf. Something reused from in the MASM's 3D remake are the visual effects. Again, with the fixed function pipeline OpenGL, my possibilities are limited, and without shaders, what I can do is mostly left for the CPU to figure out and not the GPU, so I have to be careful. As I've mentioned, we can implement a pixelization effect, the mandatory post-processing effect in all modern indie games, even if the game doesn't benefit in any way from it. For this, we render our scene into a downscaled viewport, then use GL-read pixels to read what we rendered into a texture and draw that texture scaled to screen size. Using screen textures allows for other effects, like afterimage, sometimes generalized as motion blur, by collecting and swapping a number of screen textures in an array, and also yet another, along with pixelization, omnipresent effect, the posterization, achieved by reading the pixels into an available texture color format other than RGB8, the most common one, where there are 8 bits per color, therefore 24 bits per pixel. Although I believe more proper palletization with color indexing is available for use with the fixed function OpenGL pipeline, I never really bothered to look into it, because the slide banding achieved with a 16-bit RGB565 color format was more than enough for me. As for the afterimage effect it's also used with a slide zoom and dynamic field of view to signify low stamina. By flipping through color channels using the GL color mask function while iterating the afterimage textures, we can also apply a type of chromatic aberration, though for a true version of this effect, we'd probably need to draw each texture 3 times, with each color channel slightly offset. The film grain is just a single quad that is drawn onto the screen and then scaled and translated properly in the texture matrix. Another thing that I've managed to make work was multi-sample anti-aliasing, a technique to reduce the jaggedness of lines, otherwise known as aliasing. I've added it through OpenGL architecture review board extensions, which required me to create a dummy form where I would initialize the OpenGL context, without which loading such extensions would not be possible. I then would need to load the WGL choose pixel format ARB function, with which I then initialize a new OpenGL context in another form. Getting the supported MSAA values required me to also load the WGL getPixelFormat attrib IV ARB function. The availability and visual representation of this effect sadly varies from system to system, on some being unavailable at all, on some properly sampling alpha to coverage the same way as the solid polygons and affecting the texture wrapping, on some not, leaving the foliage jagged, etc. One other useful extension is the WGL swap interval ext, which allows for adaptive vertical synchronization, which governs the rate of paint window messages being sent. This way, VSync is controllable, not enforced by default, and can be disabled, allowing for the FPS to reach the thousands if you hate your CPU cores or GPU enough. And with all the technical details aside, surely now we've reached the point where I talk about the concepts, the fun gameplay, and how I finally managed to make a proper game out of it. Except, so far, there isn't anything like that here. There isn't much interesting to be told about the MASM's 3D remake either, except probably the multiplayer. Compared to MASM's 3D in I concentrated more on the presentation this time, but still, it must be expanded further tenfold to achieve its redeemability as an interactive product. As for the story, I intend to only tell it in the game itself, and with the plans for multifacetedness, that would entail its details to be variable. I realize how detrimental to me is my focus on the narratology, story-driven framework, as opposed to the gameplay-driven ludology. And I tremble at the prospect of its crisis, which I know I can't overcome but intend to try to postpone the arrival of, yet have no means of doing that on my mind right now. I curse at my mind for not having enough creative potential to bestow upon me an easy grounding to develop my product from. Yet, at the same time, I have to learn to live with what I am and accept my own demands, as outlandish as they may be. Surely the resolutions shall come to me in the process, I say, with the naivety of a child who has yet to witness this dispassionate life crush each and every one of his dreams in a fraction of a moment. So be it, I say, with a calm and resolute demeanor, as though time were an inexhaustible gift, foolishly planning a slow and steady development process in one of the most volatile, fluctuating markets. Yet, if such goals are set before me, then I shall strive to bring myself wholly into accordance with them, and however long the path may be, I will not surrender to haste, for haste is surely the only cause that begets imperfections. Never mind the emerging subjective blindness over the long course of time. No matter how grueling and exhausting, I will realize my dream project. Surely one day it will finally happen. Surely my interest will be kept throughout the many years. And surely the product will run flawlessly on then to be modern hardware and operating systems with no bugs and glitches whatsoever. Or Windows would finally shoot itself in the head for good and everybody would just migrate to ReactOS. I look into the mirror and see before me a brazen liar, one who has boasted of the talents he claimed as his own to all who would listen, until his vanity swelled so greatly that even he began to mistake his own lies for truth. I see a man hopelessly estranged from what he is and what he longs to become, lurching from place to place in frantic defense of a crumbling image, blind to the inevitability of its collapse. He has already feasted upon its fruit, while it cracked and rotted at the foundation, a fictitious construct of one feigning craftsmanship. He knew it would not endure, so he indulged in the repose it offered, while he still could. And now, when the hour has come to prove his worth, he wakes in bitter hunger, craving more, cursing the stillness in which he once chose to remain. And as his image falls, he will still long for another relief at the end of the ceaseless process. He will go on as he always has, though now stripped of the satisfaction, the joy, any vestige of fulfillment, obedient to habit alone, clinging to the same hollow motions, because there once was a time when they gave him everything, trapped within an endless circle, forever trying to reclaim what has already passed beyond recall. Such is the nature of that wretched figure that stares back at me, and I fear to my very core that I may never find the strength to change him. For now, I'll probably be switching my focus to staying alive or taking a break and doing other projects, so you probably shouldn't expect many updates soon. I've made the GitHub repos public, but as of making this video, they are still in their extremely early unfinished states. As for this video itself, I don't know what you would do with it, and if it actually proved to be a good enough background filler, I don't really know if you should consider it an informative lecture either, though I'm happy if you've actually managed to learn something from this. Maybe just more like a devlog or a warning about what no job can do to a man. Thank you for watching, and again, thank you all very much for all your attention, be it to the older video that got very popular all of a sudden, or to any other of my projects.